Welcome to this Advanced SQL lesson. In this video, we are going to build the SQL skills you need to solve interview-style questions and real business problems. Whether you're preparing for a technical interview or trying to analyze data in your job, having a strong grasp of Advanced SQL is essential. Advanced SQL is not only about writing longer queries, it is about breaking problems into clear steps, choosing the right function, and transforming raw data into useful answers. The goal is not just to retrieve data, but to understand it deeply and use it effectively. We will cover CTEs, subqueries, window functions, ranking functions, date functions, string functions, and conditional aggregations. Each of these tools plays a crucial role in handling complex data scenarios. The most important part of this lesson is window functions. These functions allow you to perform calculations across a set of rows that are related to the current row. They are incredibly powerful and widely used in data analysis. You should feel comfortable with row number, rank, dense rank, lag, lead, sum over, AVG over, and count over. These functions help you answer very common business questions. For example, how do we find the latest order per customer? How do we detect duplicated records? How do we calculate running totals? How do we compare this month against the previous month? How do we find the top 3 products in each category? And how do we compare the current row with the previous row? By the end of this lesson, you will have a mental map of which SQL technique to use depending on the business problem. Think of this slide as your roadmap. Each topic gives you one more tool to solve problems with confidence. With practice, you'll be able to approach even the most challenging data problems with clarity and precision. Let us start with CTEs and subqueries. A CTE means common table expression. This is a powerful feature in SQL that allows you to create a temporary named result set that exists only for the duration of a query. In simple words, a CTE is a temporary named result set that you define using the with keyword. It acts like a local view that can be referenced within the main query. The main benefit of a CTE is readability. When working with complex queries, it can be challenging to follow the logic if everything is written in one long statement. By breaking the query into smaller parts, you make it easier to understand and manage. Instead of writing one huge query that is hard to understand, you can split the logic into smaller steps. For example, we can first calculate total sales per customer and call that result sales per customer. Then, in the main query, we simply select from sales per customer and filter customers where total sales are greater than 1,000. This makes the query easier to read, easier to test, and easier to explain in an interview. It also helps in debugging, as each part can be checked individually before combining them. Now, a subquery is a query inside another query. It is often used to return a single value or a list of values that can be used in the outer query. A subquery is useful when you need a quick calculation or filter. For example, we can select orders where the amount is greater than the average amount of all orders. The inner query calculates the average amount, and the outer query compares each order against that average. This approach is efficient when the logic is straightforward and doesn't require multiple steps. So when should you use a CTE and when should you use a subquery? Use a CTE when the logic has multiple steps, when you want better readability, or when you need to reuse a result inside the same query. CTEs are ideal for complex scenarios where clarity is important. Use a subquery when the logic is small, compact, and easy to understand in line. Subqueries are perfect for simple filtering or calculations that don't require splitting the query into multiple parts. Here's the challenge pattern. Find customers whose total spend is greater than the average customer spend. The hint is this. Aggregate first, then compare the customer total against the average of all customer totals. This kind of problem is perfect for practicing CTEs because it is naturally solved in steps. You can first calculate the total spend for each customer, then compute the average spend across all customers, and finally compare individual totals to that average. Using a CTE makes this process clear and structured, helping you build better SQL skills over time. Now let us talk about window functions. These are one of the most important advanced SQL topics that every data analyst or developer should understand. The key idea is this. Window functions calculate values across related rows, but they do not collapse the original rows, unlike other SQL operations. This is different from group by. When you use group by, many rows become one summary row per group. For example, if you group orders by customer, you get one row per customer. That is useful, But sometimes you still need to keep every order row. That is where window functions come in handy. With a window function, you can keep every order and still calculate values such as the customer total, average order amount, or number of orders. The main structure is function over. Inside the over clause, we can use partition by and order by. The function is the calculation. For example, sum avg count row number lag or lead. Partition by defines the group where the calculation resets. For example, partition by customer ID means calculate separately for each customer. Order by defines the sequence of rows. This is very important when you need ranking, running totals, or comparing previous rows. Look at the comparison. Group by collapses data into one row per customer. Window functions keep the detail rows and add calculated columns. For example, sum amount over partition by customer ID gives the customer total repeated on each order row for that customer. AVG amount over partition by customer ID gives the average order amount per customer. Count star over partition by customer ID gives the number of orders per customer. The challenge is to show for each order row the customer total, the average order amount, and the number of orders. This is a perfect example of why window functions are powerful. They let you keep detail and add context at the same time. Now let us compare three very important ranking functions: row number, rank, and dense rank. These functions are similar, but they behave differently when there are ties. Imagine we have sales values in one category. The values are 500, 450, 450 again, and 400. Row number always gives a unique sequential number, so even if two rows have the same value, they get different row numbers. The first 450 can be row number 2, and the second 450 can be row number 3. Rank handles ties differently. If two rows tie, they share the same rank. But after the tie, a gap appears. So the values 500, 450, 450, and 400 get ranks 1, 2, 2, and 4. Notice that rank 3 is skipped. Dense rank also gives the same rank to tied rows, but it does not create gaps. So the ranks are 1, 2, 2, and 3. This distinction is very important in interviews. Use row number when you need exactly one row, like the latest order per customer. You partition by customer ID, order by order date descending, and then filter row number equal to 1. Use dense rank or rank when ties matter. For example, if two products have the same sales amount, you may want both products to appear in the top 3. For top 3 products per category, dense rank is often a good choice. You partition by category, order by sales descending, and filter rank less than or equal to 3. Row number is also useful for duplicated records. You can partition by the business key, such as email, order date, and amount, then order by ID. The first row gets row number 1. Extra repeated rows get row number greater than 1. Those are your duplicates. The challenge is to return the top 3 products per category and identify duplicate rows in a customer table. If you can explain the difference between row number, rank, and dense rank clearly, you will be much stronger in SQL interviews. Now let us understand lag and lead. These two functions help you compare the current row with another row near it. Lag looks backward. It returns a value from a previous row in the window. For example, lag revenue over order by month gives us the revenue from the previous month. Lead looks forward. It returns a value from a following row in the window. For example, lead revenue over order by month gives us the revenue from the next month. This is extremely useful for time-based analysis. Look at the monthly revenue example. In January, revenue is 1,000. There is no previous month in this table, so previous revenue is null. The next revenue is February, which is 1,200. In February, previous revenue is 1,000, next revenue is 1,100, and the change versus previous month is 200. In March, revenue drops from 1,200 to 1,100, so the change is negative 100. In April, revenue increases from 1,100 to 1,500, so the change is 400. The formula is simple. Current revenue minus lag revenue. This gives us the difference from the previous row. When working with customers, we often add partition by customer ID. This means we compare each customer only against their own previous orders. For example, lag amount over partition by customer ID order by order date gives the previous order amount for the same customer. The challenge is this. For each customer order, compare the current amount to the previous order amount. This pattern is very common in real business problems. You can use it to detect price changes, behavior changes, revenue growth, transaction gaps, or customer activity trends. Now let us calculate running totals and moving metrics. A running total accumulates values row by row, which means it keeps adding each new value to the previous sum. For example, if the first order amount is 100, the running total is 100. If the next amount is 150, the running total becomes 250. Then, if the next amount is 200, the running total becomes 450. This way, you can track how much has been accumulated over time. To calculate this in SQL, we use sum amount over order by order date. The order by is important because it defines the order in which the total grows. Without it, the calculation would not make sense. If we want a separate running total for each customer, we add partition by customer ID. That means the running total resets for each customer. This is useful for cumulative revenue, customer spending over time, account balances, and activity tracking. Now let us talk about moving averages. A moving average smooths the data by averaging a small window of rows. For example, a 3-row moving average can average the current row and the previous 2 rows. This helps to identify trends by reducing the impact of random fluctuations. The SQL pattern is AVG amount over order by order date rows between 2 preceding and current row. This tells SQL to look at a rolling frame of 3 rows, the current row plus 2 rows before it. Running totals are great when you want cumulative numbers, while moving averages are great when you want trends without too much noise. The challenge is to calculate a running total and a 3-row moving average of sales. This type of question is very common in analytics and data engineering interviews because it checks if you understand both order by and window frames. Now let us combine date functions with window functions. This is how we solve month-over-month growth. Understanding this concept is essential for analyzing trends over time, especially in business intelligence and data analysis. First, we need to group orders by month. A common way to do that is using the date trunc function with the month parameter on the order date. This converts each order date into its corresponding month bucket. For example, all January order dates become the January month value, making it easier to analyze data at a monthly level. Extract month can be used when you only need the month number, such as 1 for January, 2 for February, and so on. Current date gives today's date, which is useful for filtering or comparing data against the current point in time. Date add and data diff help you shift dates or measure gaps between dates. These functions are particularly useful when you want to look at data from previous periods or calculate the difference between 2 dates. Now, for month-over-month growth, the process has 2 main steps. Step 1 involves aggregating revenue by month. We create a CTE called monthly sales where we select the month and sum the order amounts as revenue. This step allows us to see how much money was made each month. Step 2 is to compare each month with the previous month. We use the LAG function on revenue over the order by month to get the previous month's revenue. Then we subtract the previous revenue from the current revenue to determine the growth. In the example, January has $10,000 in revenue. Since there is no previous month, the growth is null. February has $12,000 with the previous revenue being $10,000, resulting in a growth of plus $2,000. March shows $9,000, while the previous month had $12,000, leading to a decrease of $3,000. April brings $15,000, with the previous month at $9,000, giving a growth of $6,000. The basic formula is current month minus previous month. You can also calculate percentage growth using the formula current revenue, previous revenue, divided by previous revenue. This helps understand the relative change rather than just the absolute difference. The challenge is to find month-over-month revenue growth from an orders table. This is a classic interview question because it combines several important concepts, including CTEs, date grouping, aggregation, and the use of window functions like lag. Mastering this technique is crucial for anyone working with time series data. Now let us cover string functions and conditional aggregations. String functions help us clean text. In real data, customer names, emails, cities, and phone numbers are often messy. Upper converts text to uppercase. For example, Alice becomes Alice. Trim removes extra spaces. This is very useful for emails, names, and city fields. Substring extracts part of a string. For example, you can extract the country code or area code from a phone number. Concat combines multiple strings. For example, first name plus a space plus last name creates a full name. In the string example, we clean the city using upper and trim. Then we build a full name using concat. Now let us move to conditional aggregation. Conditional aggregation means using case when inside sum or count. This lets us create multiple business metrics in one query. For example, We can calculate paid revenue using sum case when status equals paid, then amount else 0 end. We can also count canceled orders using count case when status equals canceled, then 1 end. This creates a customer-level summary with paid amount and canceled orders. Conditional aggregation is very useful for paid versus unpaid revenue, active versus inactive users, domestic versus international orders, and cleaned customer names. The challenge is this. For each customer, calculate paid revenue, canceled orders, and show a cleaned full name. This pattern is very practical because business users usually do not want raw records. They want clean, summarized, business-ready results. Let us finish with the most important advanced SQL interview patterns. The goal is to map each business problem to the correct SQL technique. Pattern 1. Latest order per customer. Use row number over partition by customer ID order by order date descending. Then filter row number equal to 1. Pattern 2. Find duplicated records. Use row number over partition by the business key and order by ID. Duplicates are rows where row number is greater than 1. Pattern 3. Calculate running totals. Use sum amount over order by order date. If you need a running total per customer, add partition by customer ID. Pattern 4. Month over month growth. Use date trunk to group by month. Use sum to aggregate revenue. Then use lag to compare against the previous month. Pattern 5. Top 3 products per category. Use dense rank over partition by category order by sales descending. Then filter rank less than or equal to 3. Pattern 6. Compare current row versus previous row. Use lag value over the correct order. Then subtract the previous value from the current value. Here are the core takeaways. CTEs make logic easier to read. Window functions keep detail rows while adding analytical context. Ranking functions solve top N and duplicate problems. LAge and lead compare neighboring rows. Conditional aggregations turn business rules into metrics. Practice these patterns with small datasets. Then increase the complexity. If you can explain the logic step by step, you will be strong in advanced SQL interviews and real data engineering tasks.